In the late 19th century, as the British Empire cast its long shadow across the globe, an invisible and lethal threat wove its own web of terror. This was malaria, the winged death, an ancient disease that decimated entire armies, ravaged countless villages, and turned fertile lands into silent graveyards. Its victims fell prey to relentless fevers and chills that shook the body to its core, often ending in the cold embrace of death. For centuries, popular wisdom had blamed something known as bad air rising from swamps. This was the origin of its name, malaria. People believed that simply breathing the air near stagnant water was enough to seal one's fate. But in the bustling and feverish atmosphere of India, a doctor in the Indian Medical Service named Ronald Ross felt a growing sense of frustration and a dull, constant rage. He had seen too many soldiers and civilians succumb to this plague, and he could not accept the traditional explanations. Ross was not actually a laboratory man by his natural inclination. He was an artist and a poet at heart, but malaria had embedded itself in his soul like a painful thorn. Something told him that the bad air theory was insufficient and that science needed to look much further. It was the brilliant Scottish physician Patrick Manson, a pioneer of parasitology, who finally lit the spark of inspiration. Manson was known for his groundbreaking work with filarial worms, and he had postulated a radical idea. He wondered if an insect, specifically a mosquito, could be the carrier of the disease. At the time, this idea seemed like pure science fiction. For Ross, however, this hypothesis was a beacon of light in the dark. He decided to dedicate himself to proving it, which began a period of intense obsession. Amidst the suffocating heat and the oppressive humidity of India, Ronald Ross embarked on what many considered a quixotic quest. His laboratory was often nothing more than improvised rooms infested with the very mosquitoes he sought to study. His equipment was basic, consisting of a microscope and his own tireless hands. Days, weeks, and months went by as he captured and dissected mosquitoes one after another. He performed this work under the curious and often skeptical gaze of his colleagues who did not share his vision. He failed again and again. He opened hundreds of tiny insects with a level of patience that was almost inhuman, but they revealed nothing conclusive. The frustration consumed him, but the image of the sick and the memory of lost lives pushed him to continue his search. On August 20, 1897, in a hot camp located in Secunderabad, everything changed. After opening a mosquito of a particular species known as Anopheles, Ross's gaze stopped on something unusual. He saw tiny pigmented structures in the insect's stomach. He asked himself what these could possibly be. This was the breaking point, the singular instant that would change medicine forever. Ross had just stumbled upon the truth that humanity had sought for millennia. He had found evidence that a small and seemingly harmless insect could carry such a devastating disease. The answer was hidden within the mosquito's own body, waiting to be revealed to the world. What he had found were, in fact, the initial stages of the malaria parasite. Those pigmented structures were the irrefutable proof that the mosquito was not just an annoying insect, but a vital link and the true architect of disease transmission. To understand the magnitude of this discovery, we have to think of the mosquito as a small biological drone. It is designed for a very specific mission, which is to transport microscopic passengers from one host to another. These passengers are the malaria parasites, and they are incredibly complex creatures. They function like tiny secret agents with multiple disguises and various escape routes to evade the body's defenses. The parasite is called Plasmodium, and its life cycle is a macabre choreography involving two main protagonists, the human and the female Anopheles mosquito. It is important to note that only the females bite, as they require blood to develop their eggs. When an infected Anopheles mosquito bites a person, it does not just extract blood. It also injects tiny forms of the parasite, called sporozoites, into the person's bloodstream. You can imagine these sporozoites as microscopic missiles. Once they are inside the human body, they travel rapidly through the blood to the liver, which serves as their first secret hideout. In the liver cells, the sporozoites transform and multiply in total silence for several days or even weeks. During this time, the infected person does not feel any symptoms at all. It is as if the parasite has set up a clandestine factory in the liver, producing thousands of new forms called merozoites. Once this factory has completed its work, the merozoites leave the liver and invade the bloodstream. They head directly for the red blood cells, which are the cells responsible for carrying oxygen throughout our bodies. This is where the true drama of malaria begins to unfold. Inside the red blood cells, the merozoites continue to multiply. Each time an infected blood cell bursts, it releases even more merozoites to infect new cells. This is the moment the human body reacts with those classic and terrible symptoms. The high fever, the intense chills, and the profuse sweating are all results of this internal battle. It functions like an infernal biological clock. The synchronous bursts of millions of red blood cells cause the repeating fever cycles that define the disease. During this process, some of the parasites transform into sexual forms called gametocytes. These are crucial for the next step of the cycle because they wait for the messenger to return. This is where the mosquito comes back into play. When another Anopheles mosquito bites an infected person who has these gametocytes circulating in their blood, it carries them away. It is as if the mosquito sucks up the seeds of the parasite. Inside the mosquito's stomach, these gametocytes mature and reproduce sexually. From this reproduction, new forms of the parasite emerge. They look like tiny microscopic worms and they migrate from the mosquito's gut up to its salivary glands. Once they have reached the glands, they are perfectly positioned to be injected into the next person the mosquito bites. This closes the cycle of infection, and this is exactly what Ross saw during his dissections. But his finding in Secunderabad was just the beginning of the journey. Ross still needed irrefutable proof that these parasites he saw in the Anopheles actually developed and transmitted the disease to a new host. Studying human malaria directly was a complex task for both ethical and practical reasons. So, Ross turned his attention to an animal model with the shrewdness of a detective. He knew that some birds also suffered from a form of avian malaria, which was transmitted by mosquitoes of a different genus called Culex. His laboratory soon became filled with cages of infected sparrows and these Culex mosquitoes. It was a monotonous and exhausting task. He fed the mosquitoes on the blood of the sick birds and then, day after day, he meticulously dissected them under the microscope. It was a titanic effort performed in precarious sanitary conditions. The temperatures in his workspace were often high enough to melt anyone's will, but Ross did not give up. He observed how the avian malaria parasites developed in the mosquitoes' stomachs, moved to the salivary glands, and finally infected new healthy birds when the mosquitoes bit again. The evidence was clear and compelling. Mosquitoes were indeed the vectors. This experiment with birds was a major milestone in medical history. It demonstrated the fundamental principle of malaria transmission through insects. Armed with this proof, Ross returned to the study of human malaria. While he had seen the parasites in the human Anopheles at first, the full demonstration of the cycle was still the missing piece of the puzzle. Other scientists, such as Giovanni Battista Grassi in Italy, were also in the same race. Using Ross's work as a foundation, they soon confirmed that Anopheles was the specific vector for human malaria. Scientific collaboration and competition were two sides of the same coin in this progress. The discovery made by Ronald Ross in 1897 was not just a scientific advance. It was an earthquake that redefined global public health. Suddenly, the fight against malaria had an identifiable enemy and a weak point that could be exploited. It was no longer about a mysterious bad air that could not be controlled, but about mosquitoes that could be fought and eliminated. The entire strategy for dealing with the disease changed radically. Sanitation and mosquito control measures became the top priority for governments and doctors. This included draining swamps and removing any stagnant water where mosquitoes might lay their eggs. It also led to the use of mosquito nets to protect people while they slept. Although modern insecticides were developed much later, the core idea of attacking the vector stemmed directly from the work Ross had done. Even the development of anti-malarial drugs improved, as the discovery of the cycle allowed for a better understanding of how treatments like quinine worked. The impact was immediate and dramatic in many parts of the world. One of the most famous examples was the construction of the Panama Canal. This massive project had repeatedly failed in the past due to the high death toll from malaria and yellow fever. It was finally completed only because mosquito control measures were implemented, saving the lives of thousands of workers. In India, Africa, and other tropical regions, the rates of infection and mortality slowly began to decrease. Behind all this progress was a man whose life was not always a bed of roses. The obsession Ronald Ross had with malaria cost him dearly, including long periods of separation from his family. The working conditions he faced in India were extreme, and he often had to contend with the incomprehension of his superiors. He dealt with a scarcity of resources and the frustration of seeing his work ignored or underestimated at times. He earned a reputation as a difficult and stubborn man, but it was precisely that stubbornness that led him to his ultimate victory. His work was finally recognized with the Nobel Prize in Physiology or Medicine in 1902. This was an honor he partially shared with other researchers who had also contributed to unraveling the mystery of the disease. It was a fair recognition for years of tireless dedication and a discovery that literally changed the course of human history. Ross, the poet who became a disease detective, had unraveled one of nature's darkest and most persistent secrets. Today, malaria remains a global threat that affects hundreds of millions of people each year. It still causes hundreds of thousands of deaths, especially among young children in Africa. However, because of Ronald Ross, we are no longer wandering in the dark. His work laid the essential foundation for all existing eradication and control efforts. Every strategy we use today, from the mass distribution of insecticide-treated mosquito nets to the development of new vaccines and drugs, is based on the fundamental understanding of how this disease is transmitted. The story of Ross reminds us that curiosity, perseverance, and the ability to look at a problem from a completely new perspective can transform the entire world. His victory over the myth of bad air continues to be an inspiration and a beacon of hope in the incessant fight for a better life for all people. If you found this journey through medical history fascinating, please make sure to subscribe to the channel for more stories of scientific discovery. For more information, visit minrora.com.